Chaos is defined as complete disorder and confusion. Behavior so unpredictable as to appear random, owing to great sensitivity to small changes and conditions. When we take a closer look at these seemingly chaotic systems, we find the opposite. Chaos theory states that within the apparent randomness of chaotic complex systems, there are underlying patterns, interconnectedness, constant feedback loops, repetition, self-similarity, fractals, and self-organization. This PBS documentary shows how this can be documented using real-world situations.
I'm going to show you how to play the chaos game. It's very simple to play, but it has an extraordinary outcome. I begin with a big sheet of paper with 3 large points marked on it, labeled 1 and 2, 3 and 4, 5 and 6. Now what I do is I choose a point at random on the sheet of paper. I'll shut my eyes to do that, and now I'll just wiggle the pen round and dab a point. There it is. That's my starting point. So now what I do is I roll the die, and it comes up with a 4. So what I do is I go halfway from my first point to the big point labeled 3 and 4. I'll mark that new point. That's my new point. I roll the die. This time it comes up with a 5, so I go halfway from my new point to the big dot marked 5 and 6, and I mark that point on the piece of paper. Now, of course, if you do this, you should use a ruler and do things accurately. You need to play it for about 24 hours or longer, and you need to play very fast. And now I roll the die. And this time it comes up with a 3, so I go halfway from my new point to the big dot marked 3, and that'll be about here. Now, of course, if you keep on doing this for a long time, what would you expect? You'd expect that you'd get an enormous mess of dots. But that's not what happens. Something very extraordinary and different happens.
Speed up the game on a computer, and this emerges. The chaos game has produced a complex and ordered geometrical structure. The revolutionary idea that a chaotic process can give rise to order is destroying old definitions of chaos we've clung to for centuries.
And here is more evidence for the digital, simulated nature of our reality.
Most of nature is composed of turbulent phenomena like the weather. Air, gas, and fluids are described by the same Newtonian equations. Over a reasonable period of time, the flow rate in this river doesn't change very much. Neither does the rock in the waterfall jump about. Yet the water never takes the same path twice. Turbulence like this has baffled scientists for centuries.
The entire universe is filled with fluids in turbulent motion. The atmosphere, the oceans, much of outer space, it basically is turbulent fluid. So one could take the point of view that you don't understand anything about the world until you understand turbulence.
For a while, this trail of cigarette smoke rises in a simple stream. Suddenly, there's a transformation. It becomes turbulent, chaotic. But what rules, if any, govern this sudden transition from order to disorder? Golub, with a partner, Harry Swinney, built this cylinder to drive fluid from simple flow to turbulence. Inside is a smaller cylinder, which can rotate at different speeds, putting an increasing shear force on water which is contained in the narrow ring around the outside. Small translucent particles suspended in the water allow us to see structure when it emerges. They start by rotating slowly.
As we increase the speed of the fluid, you will see the emergence of a pattern, emergence of horizontal lines that mark the boundaries between donut-shaped vortices. These donuts are stacked along the direction of the cylinder, and we can see them now as they start to form at a very well-defined rotation rate of the cylinder.
Water is rolling in a spiral motion sideways and up and around the donuts. As they increase the rotation rate to a well-defined level, these wavy lines develop. A subsidiary fluid motion has superimposed itself on the first, moving at a different speed. As they increase speed further, there is an abrupt change.
Okay, we've increased the speed here, and we see now for the first time the emergence of disorder, emergence of chaos in the flow. If you look on the small scale here, you can see the irregularities that mark the appearance of this disorder. The rotation rate at which this disorder appears is very well defined, just as the previous transitions were it happened at very well defined rotation rates.
The flow around the donuts is switching erratically to and fro, creating a chaotic, turbulent interference pattern at the border between donuts. When you drive natural systems into chaos, they all follow a very similar route.
Thanks for watching.